Okay, thanks so much. Yeah, thank you so very much for the introduction and also for the invitation. I mean, I'm sorry that everything was a bit complicated with scheduling, so I'm very grateful that I can give the talk today. And yeah, so as the title says, the question is what I would like to discuss with you, the impact of AI, in particular deep learning on parametric partial differential equations. I would like to show you some results. In the beginning, I would like to also briefly discuss what are the key theoretical directions in deep learning, which I see these days. And at the end, I would like to finish with a word of caution, going back to a very basic level, namely whether we can train neural networks at all to a certain extent and to a certain accuracy, which then goes into the direction of computability. Yeah, I think we all know how tremendously successful deep learning is in public life. I mean, autonomous driving, telecommunication, legal issues, not that much in Germany yet, but I mean, social decisioning is already on the go and will soon, I guess, be also taken over by neural networks and artificial intelligence, and then the whole healthcare sector. And then, I mean, if you go closer to science, I mean, there are constantly approaches based on AI and deep learning in the news, such as here on protein folding. So in that sense, I mean, there is a great drive by now these new methods, and I think this will continue also over the next years. Then, I mean, getting closer to mathematics, I mean, there was a tremendous impact already very early on, in some sense, on mathematics, starting basically around 2012. And that's also how I came to the area of AI, and in particular deep learning, because the field of imaging science, in particular inverse problems, was basically swept by these new approaches because they very easily reach state-of-the-art results and outperformed then also classical methods. The reason there being that, I mean, in imaging sciences, you don't have a rigorous model what an image is, so that makes it very accessible to learning methods. Then the area of partial differential equations was much slower to embrace deep learning. Why? Well, I mean, because, I mean, a PDE is a rigorous mathematical model, so there's a question why use these type of approaches, these learning type of approaches at all. However, what turned out is that in the very high dimensional regime, deep neural networks to some extent are able to beat the curse of dimensionality. And so then from basically 2017 on, that also took off. And now, I mean, there's an intense activity to use and analyze how neural networks can be used for solving PDEs. On the other hand, I mean, things are also not that bright. So just, I mean, yeah, in 2018, I found this a very interesting incident. It's still true today. That Ali Rahimi, who got an award at one of the big AI conferences, in his plenary speech claimed that machine learning, in particular deep learning, is still some form of alchemy. He said researchers do not know why some algorithms work and others don't. So it's a lot of trial and error. And to a certain extent, if you look at how neural networks are trained these days, it's still at that level at present. And not only is that the problem, but I mean, there are also a lot of problems with neural networks and AI in general. So, for instance, concerning trustworthiness, you see in BBC News, computers can be made to see turtle as a gun or hear a concerto as someone's voice. And then there are these examples where self-driving cars are fooled by putting stickers on traffic signs, and then they react in a non-meaningful manner and often can be forced to reach wrong decisions. So certainly, I mean, this is a serious problem. And I mean, now coming from a mathematics standpoint, for me, I mean, there are two key challenges for mathematics in that area. One is mathematics for deep learning. So asking, I mean, can we derive a deep mathematical understanding? Can we make things more robust? Can we understand why things are so unstable to a certain extent? On the other hand, deep learning for mathematics, aiming to understand how deep neural networks could improve inverse problems in imaging sciences, get better solvers, and also, which is now related more to this talk, deriving PDE solvers also via these approaches. I would now, in the next few minutes, give you a bit of an introduction into where I see the key directions of those areas, and then we will delve more deeply into deep neural networks. But I think that's also interesting for what comes next, because then the theoretical results we will show will be of a particular type of mathematics for deep learning. And so I think it's good to see once also the overview of how I view this area. Okay, so let's delve a bit deeper into deep neural networks. And since I heard you already talked a lot about this, maybe I could also keep this part a bit shorter in that direction. So everything started already very early on. I mean, neural networks are nothing new. It started in 1943 with McCulloch and Pitts, where they aimed for artificial intelligence. I mean, that's certainly a key goal and important goal. And what they did was very smart. Since humans are somehow supposed to be intelligent, at least that's what we believe of ourselves, they aimed for mimicking the functionality of the human brain, which consists of neurons and connections between those. So what they did was they introduced an artificial neuron, mimicking in some sense how a realistic neuron acts. And so you see the correspondence here. You have inputs in these dendrites, you have weights, which mimic how the dendrites maybe amplify the input signals. Then everything is collected in the somers. We have here the sum over the xi's, wi's. The neuron needs to decide whether to fire or not, which in a neural network is substituted by a bias term. And then here you have the decision whether the sum is greater than b or less than b, either it fires a 1 or a 0. And so these elements, and to see it more precisely, are connected, and the flexible parts, the parameters, are weights and biases. And later on, we will also just very briefly talk about neuromorphic computing when we come to computability. And so one at this point should also state that this is certainly an extremely crude model of what a neuron does. Yeah, and so neuromorphic computing then aims to capture much better how a true neuron acts, also involving, for instance, stochasticity and so on. Okay, but the classical neural network, the artificial neural network, is based on this. So this is the definition of an artificial neuron. We have weights, we have bias term, we have an activation function. And so this is the definition. You see it's a composition of affine linear functions and a non-linear function here, which on the previous slide was the Heaviside function. So we just fired 1 or 0, but typically one would like to keep it a bit more flexible. So one can take a very smooth function, and what is nowadays used is actually almost always the so-called ReLU, the rectifiable linear unit, which is a piecewise linear function. And for practical purposes, it's typically sufficient. Now, those you connect, maybe if you already heard a lot about those, I don't maybe need to go too much into the details there. So you connect them in layers. So each of those is an artificial neuron. And you encode it by encoding these connections here in matrices. And then you have here the bias term, then an activation function, and then you keep going. And so the general formula for an artificial neural network you see here. So it's the functions from some RD to some RNL, where NL is typically chosen equal to 1 in classification tasks. And so it's a concatenation of affine linear functions and nonlinear functions, which are, since they are univariate, applied component-wise. And of key importance is typically also the number of layers. So how many, let's say, layers we have here, which corresponds to the number of affine linear functions. So what are now the key theoretical directions in that regard? So for that, I would just to very briefly with you go on a very high level through a process how you apply these neural networks. So the idea is usually you want to learn a complicated function from which you have sample values. This function can be defined also on some lower dimensional manifold, like for instance, images. You usually assume that images are lying on some lower dimension structure, like here, for instance, images of cats and dogs, which computer scientists are always excited to separate. And so you split the samples you have into a training and a test data set. The test you set aside, the training you use for training, but then you have to decide a lot of things. for which we don't have rigorous theoretical guarantees at this point. Yeah? So how many layers do you need to take for your particular task? How many neurons in each layer? What activation function? Maybe you don't want to have something fully connected, so you need to pre-select which entries of your weight matrices you set to be equal to 0. Okay, so once you have decided that, and that's a lot of still, I mean, right now, a lot of trial and error, you then train your neural network, meaning you learn the weight and the biases. And so this is an optimization problem. We want that applying our neural network to our samples, which we know, we want that to be close to the true function value, which we also know for the samples. The closeness is given by a loss function. You can add a regularization term if you want to enforce additional properties like sparsity, for instance. Then you solve this problem by an optimizer like stochastic gradient descent, and you get the weight matrices and the biases, which gives you then a function, so a neural network. And then once you've done that, you hope that your neural network is indeed close to your F. And this now you test by using your test data sets. You apply this both sides to these xi's and hope that this is close. Okay, so that's the basic, I mean, high-level flow of how to use neural networks. They are now, I mean, that effective to a certain extent because we can train neural networks with hundreds of layers, which we couldn't do before, and also have vast amount of training data available at this point, which in some areas is actually a huge problem. Like in medical imaging, for instance, you don't have these vast amounts of training data, and so then these methods sometimes do not work that well. There are still a lot of mysteries flowing around. I mean, one key mystery is why neural networks do not overfit. Yeah, so I mean, the overfitting phenomena you might be familiar with this. You have two data sets, and if your network is not, or your model is not expressive enough, you cannot separate them. If you have more expressiveness, you are able to do a very good job. But then if you have too many parameters, the network could tend to overfit. But the surprise is that neural networks typically do not run into this mistake. And there's also these famous pictures of this double descent curve, which from a statistical learning viewpoint show that this is indeed the case, or let's say they show what happens. What the surprise is that here, if you look at the size of the neural network and the error, the training error will go down since your neural network is more expressive, and then certainly the training data can be fitted in a better way. But the test error then goes up again after a sweet spot due to this overfitting phenomena. But now in this new world of neural networks, at some point the error goes down again. And so this is called the double descent curve. This is backed up by statistical learning theory. This is still under investigation. And maybe the other, or one of the other surprises is that stochastic gradient descent works that well. You see, this is a very nice path of gradient descent without the stochasticity. It ended nicely in one of these valleys. However, if you lose stochastic gradient descent, you have a much more erratic path, and then you might end up in another local minima, which is very hard to predict. And then if you imagine optimizing over a rect landscape like this, it is a real surprise that neural networks, although the problem is highly non-convex, typically end up, the training process ends up in a very good local minimum. Okay, so what are the key directions now of mathematics for deep learning? The first is expressivity. So this corresponds to what I said in the beginning, which architecture to choose. So how does the choice of the architecture affect the performance of deep learning? And so this certainly requires a lot of approximation theory, applied harmonic analysis. It is an area which is already very advanced. Well, I mean, it started very early on. People first studied shallow neural networks, and also you exclude the training process in that field. So that makes it a bit more mathematically accessible in a certain sense. And we will see, I mean, the theoretical results we see for parametric PDEs will be in that range, in the range of expressivity. Okay, so the next question then is certainly the training process, so the learning And here, I mean, the key question is certainly that method which most people use, namely stochastic gradient descent. Why does it perform that well? What does it converge to good local minibar, although the problem is highly non-convex? Also there goes a lot of research in that area right now. Also, let's say, exotic areas like algebraic differential geometry, here to understand, for instance, how the shape of the local minima maybe affect the performance of stochastic gradient descent. So also a very exciting direction. Generalization, maybe kind of the holy grail of the area. So why do networks not overfit? What is the role of depth? Why do we see this double descent phenomena? That requires a lot of learning theory, statistics, probability theory. And so these three areas here correspond exactly to the three components of the error of a statistical learning problem. So that's the approximation error from the hypothesis class. There's the error from the algorithm itself, and then there's the out-of-sample error. Another direction I find also very exciting, it's not the main part of this talk, but I think it's a very important area, which is explainability. So I think at some point we will be able to, I guess we can do it already now, be able to buy algorithms, buy trained neural networks, and then certainly the question is how do they reach decisions? Yeah, also for instance for PDE solvers. I mean, it might be in a package, the neural network which actually solves this, but the question is how stable things are truly. And so this area of explainability now aims to derive an understanding how a particular trained neural network, which you have, reaches decisions, which features of the data are important for it. And so this is an area which to my mind requires a huge amount of more mathematics. So right now it's on very shaky feet. So there are Shapley values and so on, but still I think there's a tremendous lack of theoretical foundations at this point. And yeah, so let me also say, I mean, just as an additional comment, I mean, also the industry right now has the problem that, I mean, using neural networks for whatever you want to use it for. I think also if you now go in the direction of solving PDEs using neural networks, I mean, because of the AI Act of the European Union, you need very hard, or you have to fulfill very hard restrictions to be able to get these methods approved concerning trustworthiness. So in that sense, I mean, there is a tremendous, let's say, chance for mathematics to also get into that area. Okay, so then deep learning for mathematics, I mean, inverse problems we already mentioned. So there questions are, for instance, how to optimally combine deep learning with model-based approaches. That's one key area in that direction. And then one can also be a bit bold and ask, are neural networks capable of replacing specialized numerical algorithms at all? And the same question you can also ask for partial differential equations. So here you could go even further and ask, for instance, I mean, can neural networks also learn the PDE automatically from data, which is another direction where now, I mean, a lot of intense research starts and is already to some extent ongoing. Yeah, but here for PDE, I mean, one also other key important question is, why do neural networks perform well in very high dimensional environments? Because that is typically where they are applied, because they are most effective there. In other environments, low dimensional environments, often the classical solvers are much better. Okay, so that was, let's say, the gentle introduction to set the stage a bit. And so let's now enter the world of parametric PDEs. And here you see my collaborators, mostly from my time at TU Berlin, on the results I would like to show you here. Yeah, I guess I don't need to motivate parametric PDEs to you. I mean, so that's the key topic. It's, I mean, basically, they arise in any branch of science and engineering. And so here, just to fix notation, so you have the parameters y in some parameter space capital Y, the solution, so we denote by u, y, living in some Hilbert space, and you have the differential operator, everything depends on y, and the right-hand side will be also fy. And so also here, the problem occurs if you're in the high-dimensional regime. The computational cost might be very high due to the cross of dimensionality. So again, I mean, being a bit more specific for the concrete setting, you will consider, so capital Y, the parameter space or set, I should say, lives in Rp, where P is very large. It is compact. H, as already said, is a Hilbert space. The By here is symmetric, universally coercive, and also uniformly continuous bilinear form. The right-hand side is uniformly bounded, and also certainly, I mean, as it indicates, with the y is parameter dependent. And Uy will be then the solution, and the solution manifold we also assume to be compact. So what you certainly, I mean, in the first instance, typically do if you want to solve this. So also just to fix notation here, you bring it down to the finite dimensional setting. And so here the notation we want to use is the high fidelity space we will call Uy. So that lives in the Hilbert space, and the dimension of UH. So okay, let's say it again. So the high fidelity discretization space we call UH, and the dimension of it will be capital D, which is finite but typically very large. And so the solution in that setting, in the finite dimension setting, will be called UYH. And so there's CS lemma that it's the best approximation of Uy by elements in UH. And I mean, we also all know how the Gerken solution looks like. Again, to fix notation. So we have for a basis for UH, and then the solution satisfies. So these are the coefficients of my basis, and then this is the stiffness matrix BHY inverse times the right-hand side, which here we call FYH. Okay, so now, I mean, the question is, I mean, what do we want to use neural networks for in this setting? Okay, so we have this parametric map. We brought it now to the finite dimensional situation. So I have my parameter here, y in capital Y, which lies in Rp with a large P. And we want to map that to the coefficient vector UYH, which now lives in Rd, where D was the dimension of the high fidelity discretization. And so the question now is, we want to ask is, can we neural network approximate the parametric map? What are advantages? Well, I mean, it's a universal flexible approach. After we've trained it, I mean, we can compute it rapidly. And yeah, so the key point is that it's, I mean, certainly one would also like to analyze whether neural networks are actually capable of solving this task. And we will see that this is the case. The precise question we are asking here is, if we are given an accuracy, can we find a neural network which approximates the solution? So, I mean, this should be phi of y. So if I input my parameter, does the neural network then approximate the solution up to that epsilon for any parameter? Yeah, so that's a question of expressivity, as I said before. So it's entirely a question of approximation theory. This does not tell us, if we train a neural network, that this actually performs the task. Yeah, so this is just an existence result. And certainly in this regime, we can also ask, how does the complexity of this phi, psi depend on, phi depend on P? And so P was the dimension of the space where the parameter set was embedded in, and capital D, the dimension of the high fidelity discretization. Now, then it would be certainly nice to also analyze the training algorithm. This was that point out of reach. Instead, I mean, what we did was we performed extensive numerical experiments to check how neural networks perform numerically on this task. I mean, certainly there's a ton of research already on PDEs, where usually the approach, and I'm sure you discussed this extensively, is always to replace or approximate the solution by a neural network, use the neural network then in a certain extent in the loss function. And also solving PDEs, I mean, there's a ton of work, maybe to some extent, I mean, the closest is the beautiful work by Chris Schwab. Okay, so I said this is an expressivity question, so let's briefly review expressivity of deep neural networks. This is again the definition for a neural network we already saw on the previous slide. So the first question we now need to ask is, how do we define complexity of a neural network? Because, I mean, for approximation, you will always look at approximation with low complexity. And typically, I mean, if you look at classical results using best entire approximation, then you aim for sparsity. So the question is, for which measure of complexity do we aim for here? And here we aim for, well, measurements for size, or I mean, how memory efficient the neural network is. So this measure counts how many non-zero entries there are in the weight matrices and the bias vectors. Certainly this is not the only measure for complexity, it is a measure. No? I'm not claiming that this is the best in any way. It is the measure which a lot of people choose. Okay, so this is a measure, as I said, related to memory efficiency, if you want to store your neural network. Okay, so I mean, there's a very classical result in this range, which you might have also already seen, the universal approximation theorem. It was maybe the first highlight in that area, which tells us if we have a continuous function on a compact domain, the activation function is continuous, not a polynomial. Then for every accuracy, we can find a neural network which approximates that f with that accuracy. And so these neural networks are shallow neural networks, one says. They have one says hidden layer. Yeah, so you see here, this is the affine linear map, which encodes these first connections. Then we have an activation function here, and then we sum over these terms, which give me this part. And so I have this one layer or two layers phenomena, depending on how you count neural network. Okay, so with shallow neural networks, you can actually do a lot, but I mean, here the complexity can be arbitrarily large. So this result doesn't constrain that in any way. There are a lot of other results. For instance, I mean, Jarodsky has beautiful results in that area. So for instance, here for continuous function, S times continuously differentiable functions, here you see people already consider now the ReLU, the rectifiable linear unit, which I mentioned is in some sense the state of the art for activation functions. And so this result is already closer to complexity measures, because here the distance is precisely measured by the complexity of the neural network 2 minus S divided by D. So the D appears in a bit unfortunate way here, not showing that, I mean, because of dimensionality in some sense it's hidden. Still, I mean, I think it's a really nice result because it now connects the accuracy with the complexity in a direct manner. Yeah, I mean, but this is not, in a way, it doesn't show that some lower bound is met or that it is optimal in a certain manner. Also, I mean, a key question in this whole area is, I mean, what are good and correct function spaces? I mean, there are some work, for instance, we have some work in that direction, but still, I mean, this is the main question. I mean, then if you apply it to PDEs, you don't have this problem anymore, because you have much more knowledge about the function spaces. But in general, in this area of deep neural networks, that is also one question. What are realistic function spaces where you would like to train your neural network, or say it that way, I mean, which contains functions which you want to learn with your neural networks. So if you aim for an optimality result, you need lower bounds. And so let me mention, I mean, just one result. where one can actually indeed show that the lower bound is met, and which also relates to the complexity. So here, this is a predecessor for this result. We have a very precise lower bound and can then show that this lower bound, we can exactly compute neural networks which in that sense attain this lower bound. And as a sideline, this basically also shows that neural networks perform as good as all previous systems like wavelets, shieldeds, and so on, which we designed perform concerning approximation accuracy. Okay, so but this doesn't tell us about dimensionality. So I mean, there are a lot of other results, which I'm sorry if there are a lot of people in the audience whose results I don't mention. I mean, this is a very rich area. So I just want to show you, I mean, a couple of, let's say, considerations one takes in this field. So let's go back to parametric PDEs. That was our question. And we now want to ask, so that was a parametric map. So these are the questions. And now we want to focus also on ReLU neural networks. And for that, to show you the result, let me also briefly recall the reduced basis method, which I guess, I mean, you're also familiar with. You have your continuous solution manifold, you discretize it, and then you have the offline space where you take snapshots, and the online phase where you then compute solutions also for new parameters. Okay, so this is, let's say, the higher level viewpoint. The a bit more detailed viewpoint is this. So one assumes that there exists a low-dimensional space, a reduced basis space, now with a lower dimension, and also to fixed notation. The dimension of the reduced basis space we call little or small d of epsilon. And so this is a very standard assumption in that area, that, I mean, the continuous true solution can be for any y approximated with, in a certain sense, arbitrary accuracy by elements of this reduced basis space, so in a sense that lies in a very fortunate manner in this very high dimensional space. And so then, I mean, you can transfer between the reduced basis space and the high fidelity space by a transformation matrix. So remember, this was our basis for the high fidelity space. This is now for the low dimensional space. V is the transformation matrix. And we can also then derive the stiffness matrix, the right-hand side, in this reduced basis scenario by this transformation matrix. And so the Galerkin solution, also this is rather standard. You can express this in this high fidelity, the basis from the high fidelity space, by this coefficient sequence. Okay, so now what one can show is the following. So please first take a look here. One can show there exists a ReLU neural network of this size, so that it indeed approximates the coefficient sequence of the high fidelity solution up to an arbitrary epsilon for any parameter. Yeah, so this was what we aimed for. Now taking a look at the size, so the complexity, you see that it's also benign. It depends polynomially on the dimension of the reduced basis space, cubically, yeah, polynomially cubically. It depends linearly on the dimension of the high fidelity space, and it also depends polylogarithmically on epsilon. Now you have certainly, I mean, a couple of assumptions you need to satisfy. The first assumption is the assumption from the previous slide that there exists a reduced basis space, which then in some sense one hopes the neural network senses, but the space has to exist. If it doesn't exist, I mean, you have a problem. And also you have neural networks which approximates the forward operator here, the stiffness matrix, the right-hand side, up to a certain accuracy.
Gitta, can you hear me? There's a question in the room, Gitta.
Yeah.
Hi, Gitta, this is Fabio. Just one question. What is, I mean, this network, what is the input and the output you're trying to reconstruct the solution on a single point, Ex, the domain, or the whole function?
Yeah, this is, sorry, that's a good question. So here it should be phi of y.
So the input is just y in the parameter, and the output is the whole solution.
Yes. It's the coefficient vector, yes.
Thank you.
Okay, so we also have a different version, which is then, I mean, to a certain extent, an extended version. You need to pose some conditions then on the continuous solution. This requires additional properties of the situation. So here, what you require is that there are neural networks which approximate these. Sorry. The basis from the reduced basis space up to a certain accuracy. Yeah, and I mean, these assumptions which you saw, some might look a bit restrictive, but you can show that they are, for instance, satisfied for diffusion equation, linear elasticity equations, and so on. Okay, so these are expressivity results. They show indeed that neural networks are able to approximate this parametric map, and the complexity of the neural network behaves, let's say, in a nice way, depending on all the dimensions we are involved. I mean, we see. The proof itself, I mean, I don't want to go too much into the details, also due to time constraints. Let me just say the main task, it's, yeah, so as every time with expressivity results, it's a constructive proof. We explicitly construct the neural network which approximates now the solution. So the key task is to approximate these coefficients. That is done in stages. So first, scalar multiplication is approximated by neural networks, and so one can build on results by Jarotsky, who showed how the square function can be approximated by neural networks. And then from that, one can deduce it for the product of two scalars. From that, one can do matrix multiplication. And you see here, we are not taking the best algorithm, but D to 3 is sufficient. From there, you can go to inversion and analyze how neural networks can approximate the inverse operator. And each time carefully, as you see here, tracking the size of the neural network, which is important for that. Yeah, and so then, I mean, you basically, that way, you can, so sorry, if you go back, yeah, so you see this is a combination of matrix multiplication and inversion. And what you then take also into account is the assumptions on B itself and the right-hand side, that those can be approximated by a neural network of a certain size. And so then from that, you can then deduce these two results. And so it's a very, I mean, it's a very technical construction, in that sense, very involved. But mainly the key idea is to explicitly construct neural networks which achieve this task, tracking the size and the complexity. Okay, so numerical experiments already said. I mean, one would, or we would love to have also a theoretical result on.
Gitta, sorry, may I ask another question?
Yeah, sure.
In your construction, if I understand correctly, you have hard-coded in the neural network the, let's say, optimal reduced basis. Is that?
Yeah.
Okay.
So there, yeah. So as I said, I mean, it's an expressivity result. So later on, I mean, when you train the neural network, you don't need that. But here, yeah. So for that, I mean, you assume, and that was also the assumption of the theory, that you have that. Okay, so now, I mean, concerning learning problems, the question is if now one can throw everything overboard, what was done theoretically, and the world is suddenly very different. So the goal is now to analyze how these approximation-theoretical results can be also seen in practical learning problems, and whether they give indications about those, or whether they are, let's say, very far off and just abstract results which do not have anything to do with the real situation. And so for doing that, I mean, one has certainly a lot of problems because one would like the tests all to be comparable. Yeah, so the question is, I mean, how does the sampling procedure affect the test, the optimization procedure, the quantification of the complexity, and so on. And this is usually also a problem in the whole area of deep learning, that tests are not reproducible and everything is a bit shaky. So what we try to do is to keep the architecture for everything fixed. We always chose the same one. We established independence of the sample generation, and you will see that there are a lot of, I mean, test cases which are carefully designed. And we wanted to test certain hypotheses in the numerical experiments, whether the performance suffers from the curse of dimensionality or not, whether it's sensitive to parameterization, and how learning is affected if the parameterized problem is non-affine. So these were the hypotheses, and we will see then in the end whether this is true or not. I mean, again, saying there are a lot of other results in that direction, but I mean, we here were specifically looking at parametric PDEs and specifically testing our approximation-theoretical results. Okay, so this was the test setup. We took this parametric diffusion equation, and as said, so defined on 0, 1 squared with 0 boundary conditions. This is the parametric map, which we now want to learn. We varied then the type of parameterization, the dimension of the parameter space, and the complexity of the additional hyperparameters. So again, being more specific, so this is our setting, the parametric diffusion equation, which we now analyze. So that's the right-hand side here. It's a simple polynomial. We look at affine parameterizations and non-affine parameterizations. Here we have different types: trigonometric polynomials, chessboard, partition, cookies with fixed radii, and then in that range, cookies with variable radii, and clipped polynomials. And so for all of those, we always took the same architecture and so on. And so the precise setup is here. The finite element space, you will say, well, I mean, this is really coarsely sampled, but otherwise, I mean, the numerical experiments would be just too huge and would have taken too a long time. We just wanted to prove the point here. The fixed neural network has 11 layers, and here is the number of neurons in each layer. Yeah, so you start inputting, and that is also related to one question which was asked. You input here the parameter, you output the values on the grid points. That's the activation function, and here's the learning procedure. It's always fixed training set, a fixed number of training samples. We fixed how the neural network is initialized, we fixed the loss function, we fixed the optimization procedure, and the dimension varies for parameter sets up to 91. Okay, so here are a couple of results which we derived. This is now in the affine situation for trigonometric polynomials. What you see here is the parameter dimension. This is the relative test error, and you see that this is a nice linear behavior. Yeah, so which certainly depends on this parameter. Yeah, sigma, which you see here. So the hyperparameter of the whole, yeah, so the sigma here, which is the hyperparameter, which we also said we want to vary. But still, I mean, you don't see any exponential behavior. It is a linear behavior growing with the parameter dimension p. This is again affine. Now chessboard partition again, I mean, you see this linear behavior in the parameter dimension p. And what you see here in addition is the training, and you see here, remember, we have always a fixed training, a fixed neural network which we train, but you see that still, although this is in a certain sense restrictive, the training error goes down very nicely, very smoothly over the epochs in relation to the mean relative error. So everything behaves in a very, very nice and smooth manner. And the same also in the non-affine situation. Also here, you see the parameter dimension grows linearly. And again, the training procedure is very benign and behaves very nicely. Yeah, so in that sense, I mean, the network seems to there, I mean, behave in a certain sense similar to affine and non-affine parameterization. So from that, one can conclude numerically, yeah, so it's certainly not a proof, but I mean, in the experiments, we saw that the performance does not suffer from the cross of dimensionality. It is sensitive to the parameterization, certainly, I mean, but in that sense, that is doesn't suffer from the cross of dimensionality. And learning is also efficient for the non-affinely parameterized problems. So there's no fundamental difference between those. So in that sense, for the neural networks, it doesn't matter that much whether you have an affine parameterization or a non-affine parameterization. Okay, so I would like to just use the last maybe 2 or 3 minutes to finish with something which I find also very, very exciting. Because you can then also ask, now you need to train your neural network. Can you actually do that in a, how to say, meaningful manner? So we now go back to the very basics and look at computability aspects. And that's joint work with a colleague from TUM, Olga Bocho, whom some people might know, and one of my PhD students. Okay, so now, I mean, we train a neural network on a digital machine. So what we have in front of us, the laptop is a digital machine, and we call it a computable problem if this input-output relation can be computed on digital machines, which are usually modeled as a Turing machine for any given accuracy. So that's computability theory in its, let's say, most basic form. And now we can ask whether neural networks can actually perform this task, which we just saw from this computability viewpoint. And then you see something very astonishing. You can actually prove that the solution of a finite dimensional inverse problem, and if you solve a PDE, I mean, you solve to some extent also an inverse problem, is actually not Turing computable, particularly not by a neural network. It's even more, it's what's called Banach-Mazur, not Banach-Mazur computable, which implies non-Turing compatibility. Yeah, and so the effect of that, we see that a bit more detailed on the next slide, is that, I mean, even if you have theoretical maybe guarantees for the outcome, which we actually don't even have here because we just have these expressivity results, but let's assume I have theoretical guarantees for the training procedure. Because this is not computable, I cannot tell whether I'm in that range because I just cannot compute it. Yeah, so no algorithm exists which on digital hardware derives neural networks approximating the solution for any given accuracy. So that means the output of such a neural network is per se not reliable. There are no guarantees. And so this could point towards why there are instabilities or non-robustness. So there is a subtlety here. If you have a given accuracy, I mean, then you can, for that specific accuracy, design an algorithm. What you want is certainly an algorithm, a type of algorithm, which gives you that for any accuracy. So that's a huge limitation of today's hardware. And so the question is what to do. And now pointing again to what I said in the beginning, there are now new computing models like neuromorphic computing. So Intel just funded a huge new company here in Germany, also biocomputing, which in some sense significantly extend what digital hardware is capable of to a more analog situation. And so now I can ask the same question as before on the previous slide. What about now? And so what we could prove there is that in fact, the solution of finite dimensional inverse problems is actually computable on such an analog machine. Yeah, so this shows that, I mean, there is actually also from this viewpoint a great need to go in that direction, because otherwise all the theoretical guarantees we have and we worked hard on, I mean, if it then comes to numerical computations, well, I mean, they don't tell us anything because we cannot compute it. Okay, so let me finish with some final thoughts. I mean, I think this area of deep learning, I find it very exciting. We see impressive performance of real-world applications. The theoretical foundation is largely missing. There are some key directions concerning mathematics for deep learning, expressivity, learning, generalization, explainability, and certainly more, like also robustness. And then deep learning from mathematics, we delved much more deeply into the area of partial differential equation. I showed you some upper bounds on the complexity of ReLU neural networks to approximate parametric maps. I showed you numerical experiments, which showed that also numerically, it seems that things are benign and the performance does not suffer from the curse of dimensionality. But in the end, I mean, what one also has to keep in mind is that there are actually problems right now with the hardware we use, with digital hardware. If we solve here, we showed that for finite dimensional inverse problems, which are typically also one part of a solver of a PDEs, because for digital hardware, you can show that it is actually not computable. And with this, I'd like to close, and thanks a lot for your attention.